Welcome everybody. Thank you for joining us this morning for the first instalment of our two-part methylation series. My name is Anastasia and I'm a clinician educator at Genova Diagnostics Europe. And I'm going to be taking you through today's and next week's webinars with the aim of helping to increase your understanding of how methylation works, what kind of imbalances may manifest into various clinical pictures, and of course how to interpret Genova's methylation panel, which combines both genomic as well as functional analytes related to methylation pathways. So lastly, I'll also be covering some case study examples in next week's instalment where methylation testing has proven to be valuable. So the aim of today is to cover an introduction into methylation, the basics of what methylation actually is, and then we'll be going systematically through each part of the main processes in methylation, such as the folate cycle, the methionine cycle, and the transulation pathway, and how each of these pathways interlink and the role they play in various key physiological processes. And finally, at the end, I'll also be highlighting the type of patient that would benefit from methylation testing and the symptoms that can point to methylation imbalances so that you as a clinician feel more confident in recommending the test. So what is methylation? Simply put, it is the transfer of 4 atoms, 1 carbon atom and 3 hydrogen atoms from one substance to another. And this here, what you're seeing in the middle, is what we call a methyl group. So think of methyl groups as substances that act like billions of switches, which do things like turn genes on or off. They help to regulate mood, detoxify hormones, produce energy, and promote healthy aging. So methylation really does play a ubiquitous role in the body, and it's a biochemical process that happens billions of times per second in every cell of the body, where methyl groups are being transferred and donated between different molecules which change their structure and function. We also know that nutrients such as vitamins and minerals and amino acids from the diet are needed to keep these processes running smoothly. And of course, there are also genetic factors at play, as well as oxidative stressors, which can affect how well these pathways work. And these are the factors that I'll be covering extensively throughout today's and next week's webinars. So aside from a few of the physiological processes that I have just listed, as you can see, the list really does go on, which really highlights how important methylation is in the body. So for example, we have creatine production at the top right-hand side here. And this is a substance that's found naturally in muscle cells. It helps your muscles and cells produce ATP. There's also DNA synthesis and gene regulation. I've already mentioned hormone regulation and also detoxification. So we're also talking about the detox processes related to environmental toxins. Cell membrane repair and myelination are also involved in methylation. So that's quite important in relation to cognitive function and the nervous system. And then finally, you also have other factors such as fat metabolism, immune function. I've already mentioned about neurotransmitter production and metabolism in relation to mood regulation. And then lastly, we have nitric oxide production and vascular endothelial function, which of course is essential in the context of cardiovascular health. So as you can see, this just reiterates how globally important methylation is. And I'm sure some of you are already thinking about what kind of patients would benefit from having methylation testing done. So to keep these processes functioning optimally, there is a necessary balance between many different biochemical pathways. And what is termed the methylation cycle involves an interplay between folate metabolism, methionine metabolism, and homocysteine transulation. And the body continuously adapts these interconnected pathways in order to maintain homeostasis. However, key amino acid deficiencies, a lack of vitamin and mineral cofactors, genetic enzymatic predispositions, and a wide array of oxidative stressors can impact multiple enzymes, leading to a disruption in a patient's overall methylation status. So now that I've given this short introduction into methylation and what it actually is, let's move on to the first part, which is the folate cycle. So this here really is the first stage of the folate cycle. What actually happens when, from the minute we ingest folate is just as essential as looking downstream to the end product of the folate cycle, which is a compound which I'm sure many of you are familiar with, which is 5-MTHF or 5-methyl tetrahydrofolate. So in the diet, folates exist as polyglutamates, and these need to be enzymatically converted into folate monoglutamate in the jejunal mucosa, so that's in the small intestine, in order to be absorbed. And it's worth noting at this point that synthetic folic acid, which is used in supplements, is actually twofold better absorbed than dietary folates in the intestine. But this, of course, doesn't mean that it's better or that we should all be supplementing with folic acid. And I'll be talking a bit more about this in the next few slides. So neither dietary folate nor folic acid are biologically active until they are converted to tetrahydrofolate in the liver by the enzyme dehydroreductase or dehydrofolate reductase in the liver, that's DHFR. And as you can see, this is illustrated here. So once folate or folic acid are biologically active, so you've got the DHFR enzyme here, they will then enter into the next stage of the folate cycle. And as you can see, there are various steps that determine the conversion of dietary or supplemental folic acid into the end product, which is 5-MTHF, this one here. And that obviously goes into providing a methyl group to the methionine cycle, which converts homocysteine into methionine. So the light blue squares here, they represent specific enzymes that are actually responsible for propelling the conversion of folate eventually down into methylfolate. And you can also see various nutrients and amino acids that serve as cofactors for various enzymes, such as B6, iron, B2, and B3. And they are listed here in the small text, as you can see. It's also worth highlighting that 5-MTHF is the predominant circulating folate in serum, and there are other non-circulating forms of folate precursors, such as 5,10-methylene tetrahydrofolate, that's this substance here, and this is mainly found intracellularly and rather than in serum, and is also just as important. So before I go further down into the folate cycle and the various enzymes that are responsible for the conversion of folate or folic acid into 5-MTHF, I wanted to do a brief slide on folic acid, supplemental folic acid. So I mentioned that whilst folic acid is better absorbed twofold than dietary folate, it doesn't mean it's better. And this is why. So the DHFR enzyme has relatively low and variable activity in the liver. And when it comes to folic acid, the rate of that activity can be significantly lower. And not only that, but taking folic acid can increase the amount competing for the DHFR binding sites, which can actually crowd out dietary folate. So what this does is it sets up the possibility that a high intake of folic acid may result in elevated levels of unmetabolized folic acid in the bloodstream. And the debate as to whether unmetabolized folic acid levels contribute to disease is ongoing, and the literature is varied. But these are just some of the potential negative health consequences that may be associated with unmetabolized folic acid. So we have reduced numbers and activity of natural killer cells, and therefore an impact on the immune system. Possible increased risk of cancers, and specifically the acceleration of preneoplastic lesions. Some scientists have hypothesized that unmetabolized folic acid might be related to cognitive impairment among older adults. And then lastly, high levels of supplemental folic acid in preconception were associated with lower scores on several tests of cognitive development in children aged 4 to 5 than in children of mothers that took lower levels, such as between 400 mcg and 999 mcg. So what about folinic acid? Some of you may have also heard about this type of folate or supplemental folate. The great thing about folinic acid is that it can readily enter the folate cycle without being reduced by DHFR. So for those with polymorphisms on the DHFR gene, this may be a more effective way of supplementing. It also seems to be anecdotally more gentle than supplementing with methylfolate for those that are sensitive to methylfolate, which is actually quite common, especially in psychiatric conditions where neurotransmitter imbalances are concerned. So let's go back to the folate cycle to pick up from where we left from. So dihydrofolate reductase converts folate into tetrahydrofolate. We're just here at this section. And tetrahydrofolate then gets metabolized by SHMT, this enzyme here, using serine as a methyl donor. And after donating its methyl group, as you can see, it becomes glycine. However, as you can see, the arrows are pointing upwards and downwards for this particular enzyme, and this is to illustrate the reversible nature of this reaction. So think of the 5,10-MTHF, this one here, as a branch point in the cycle, and the direction it takes depends on methylation demand. So the first direction is down into converting, as you can see, 5-MTHF, 5-methyl tetrahydrofolate for methylation. And the other direction is purine nucleotide synthesis, as you can see, the arrow pointing down this way. And this plays a role in DNA and RNA formation, as well as ATP and NADH formation, among other important compounds. So when methylation demand is normal or low, this acts as a negative feedback loop to MTHFR by slowing down MTHFR creation and allowing folate to be used for purine nucleotide synthesis, and therefore DNA replication and repair. So as you can see, this enzyme here, SHMT, is dependent on B6 and SAM, and iron. And the enzyme gives metabolic priority to nucleotide synthesis over SAM synthesis. And this is why it's implicated not only in disturbances in the methylation cycle, but also in conditions such as cancer, where, for example, polymorphisms on the SHMT enzyme can lead to genome instability and an overexpression of oncogenes and the inactivation of tumor suppressor genes. So finally, the end product of the folate cycle, as we all know, is methylfolate or 5-MTHF. And this provides a methyl group to the methionine cycle for the conversion of homocysteine to methionine. And methionine will eventually be converted into SAMe. And SAMe is the sole methyl donor in more than 100 different reactions catalyzed by methyltransferase enzymes. So SAM is found in every cell of the human body and serves as an important biological function in activating the transulation pathway, resulting in glutathione synthesis and energy production. And some of the methyltransferase enzymes include the following, but aren't limited to: DNMT, involved in DNA methylation and the switching on or off of genes; HNMT, involved in the breakdown of intracellular histamine, and so of course plays a significant role in someone's susceptibility to environmental sensitivities, seasonal allergies, etc. COMT, which I'm sure many of you are familiar with, which involves the detoxification of catechol compounds, and therefore compounds such as dopamine, noradrenaline, and adrenaline, as well as estrogen. And we know that a deficiency in 5-MTHF and a slow COMT enzyme can result in symptoms of excess estrogen and an amplified stress response. PNMT, involved in the conversion of noradrenaline to adrenaline and therefore plays a role in healthy adrenal function. ASMT, involved in the production of melatonin and therefore involved with healthy sleep cycle function. PEMT, involved in the production of phospholipids, healthy bile composition, gut health, and cell membrane structure, so important in the context of cognitive health as well as other issues. And then finally, GAMT, involved in the production of creatine, which we've already mentioned plays a role in muscle recovery from exercise as well as energy production. So these are just some of the methyltransferase enzymes that transfer a methyl group from SAM to their substrates in order to catalyze a specific reaction. So based on this and the various functions of these enzymes, you can only imagine what the impact would be if there was a lack of SAM production due to issues perhaps upstream in the methionine cycle or the folate cycle, and how this could manifest clinically from person to person. So now I've covered the folate cycle, I want to move on to the next part, which is looking at the methionine cycle and go over how these cycles interconnect to eventually help produce SAMe through the recycling of homocysteine. So here we've zoomed out and we can see where the folate cycle connects with the methionine cycle. So just here. So the purpose of the methionine cycle is to convert homocysteine into methionine, which then becomes SAM, the end product of methylation, just here. So as you can see, the first enzymatic junction between the folate cycle and the methionine cycle is MTR, this enzyme here. And this enzyme requires methylfolate as a methyl donor and methyl B12 as a catalyst to convert homocysteine to methionine. However, you'll also note that there's an additional enzyme, MTRR, on the right-hand side of this cycle, and this enzyme here is responsible for maintaining adequate levels of activated or methylated B12. So generally speaking, any SNPs or variations on this enzyme here, the MTR enzyme, have an upregulating impact, meaning that if this was playing out in real time, we would see an upregulation of homocysteine conversion to methionine. However, if there is a lack of activated B12 or methylated B12 going into this enzyme here, it won't be able to effectively do its job in homocysteine recycling. So this could effectively lead to a backup in homocysteine. So we also have the middle of the methionine cycle, which is often thought of as the salvage pathway for homocysteine conversion. And this is sort of the backup or the plan B pathway. And this is because when methylfolate levels are low, whether it's due to a dietary deficiency or whether it's due to SNPs downregulating methylfolate availability, the salvage pathway or the BHMT pathway is there almost as a backup for providing methyl donors for homocysteine to methionine conversion. And as you can see, this pathway is dependent on choline oxidation to betaine, which is just here. And then betaine is used as a methyl donor to convert homocysteine to methionine via the BHMT pathway. As you can see, zinc is also a cofactor for this enzyme to function optimally. So as you can see, also the product of the BHMT pathway is DMG. So once betaine has donated its methyl group to the BHMT enzyme, it becomes DMG. And when DMG is elevated, this can act as a negative feedback loop by inhibiting BHMT. So as you can see, there's always this fine balance between the activity of the enzymes and the availability of cofactors going on in order to continuously reach homeostasis. So homocysteine, the main point, of course, of the methionine cycle is to convert homocysteine to methionine to then eventually produce SAMe. And as I'm sure many of you know, controlling homocysteine levels is one of the main ways that we gauge someone's methylation capacity. It plays a fundamental role in methylation. Of course, it's a major branch point in the methylation pathway. And as we already know, as we've already gone through, it's either converted to methionine, through the methylfolate and methyl B12 dependent pathway, or the BHMT or salvage pathway, which is illustrated here in this diagram. And there is just one more route that homocysteine removal can go down, and that's the transulfuration pathway, which I'll be covering in the next few slides. So homocysteine is not a classic amino acid found in dietary protein. It comes from the demethylation of SAM. And under normal conditions, the body will remethylate homocysteine several times before allowing irreversible transulfuration. So this means once it's been removed down the transulfuration pathway, there's no going back. So it's removed permanently. So being the important biomarker that it is in relation to methylation, homocysteine is often tested to gauge someone's methylation capacity. And we also know that, of course, high homocysteine carries its risks. So I mentioned there are some significant risk factors, and here are some of the important ones. So elevated homocysteine can enhance vascular smooth muscle cell proliferation. It can increase platelet aggregation and acts on the coagulation cascade and fibrinolysis, causing normal endothelium to become more thrombotic. So in a nutshell, it can contribute to the development of atherosclerosis, as well as other cardiovascular diseases. Elevated homocysteine has been shown to induce inflammatory cytokines and contribute to disease progression. Homocysteine can also impair bone health, and it can do this by interfering osteoclast activity. And it does that by impairing the cellular and molecular mechanism of bone marrow-derived osteoclasts. Elevated homocysteine increases the central nervous system phosphorylated tau, leading to increased neurofibrillary tangle formation seen in Alzheimer's dementia, which is, of course, the hallmark of dementia. Finally, we also know that elevated homocysteine can interfere with methyltransferase enzymes. So it can actually have an inhibitory impact on methyltransferase enzymes related to neurotransmitter synthesis and or the breakdown of neurotransmitters. We also know that homocysteine does have some neurotoxic properties, so important in relation to brain health. So what actually causes homocysteine, high homocysteine levels? So we already know that a lack of those cofactor nutrients for both pathways in the methionine cycle can lead to a backup. So as you can see, that's these nutrients here: methylfolate, methylcobalamin, some of the B vitamins, zinc, choline, and iron. And then we have the SNPs. or the single nucleotide polymorphisms, which may lead to a downregulation in the activity of certain enzymes. So for example, the SHMT enzyme, which we've already spoken about, which when downregulated can limit the availability of folate to act as a substrate for MTHFR. And then we have the MTHFR enzyme itself, which when downregulated will limit the availability of 5-methyltetrahydrofolate for homocysteine conversion. We have the MTRR enzyme, which when downregulated can limit the availability of methylated B12 for homocysteine conversion. And then finally, we have the BHMT pathway, which will prevent the functioning of this backup pathway for homocysteine conversion. So there are also other factors that can lead to an accumulation of homocysteine, and that's related to lifestyle factors such as a high alcohol intake, tobacco use, and a high intake of caffeine. So I've gone over why elevated homocysteine can be a problem, but what about low homocysteine? So it's worth noting that low homocysteine levels and the clinical associations with this aren't well represented in literature. However, because homocysteine is actually used to make glutathione, and this is illustrated here in this pathway at the bottom, which is the transulation pathway, that could effectively lead to issues if there were low levels of homocysteine, such as a low level of glutathione production. We also know that there are a couple of factors that can contribute to low homocysteine. So one of them is dietary intake of protein, a low dietary intake of protein, and of course poor absorption of protein. There may also be an upregulation in the transulation pathway, which may deplete homocysteine levels, but we'll get onto this in the next few slides. I should also add to that you know, if homocysteine is low, then of course the main issue for that is that there will be lower levels of methionine, and then of course lower levels of SAM. So that's, you know, probably the most important factor there to highlight. So once homocysteine is converted to methionine, methionine is then converted into SAM, and this is done via the MAT enzyme, or the methionine adenylyl transferase enzyme. And as you can see, this enzyme here depends on ATP, magnesium, and potassium. So a depletion in any of these compounds or nutrients can downregulate SAM production. There's also the possibility that someone can have a SNP in the MAT enzyme, which has a downregulating impact on the activity of that enzyme, and that of course can lead to a depletion in SAM as well. So we finally get to SAM in the methionine cycle. SAM is tightly regulated in the liver. And when SAM levels are elevated, this acts as a negative feedback to MTHFR. So it inhibits the activity of MTHFR as well as BHMT. And this is, of course, to sort of maintain homeostasis and prevent a hypermethylation picture. High levels of SAM have also been associated with adiposity and obesity, although the mechanism of this association is still being studied. So the final part of the methionine cycle is SAR and SAM, the S-adenylyl homocysteine production, as you can see at the very bottom here. And this is the end product of methylation reactions and a metabolic precursor to homocysteine. So once SAM has donated its methyl group to methyltransferase enzymes, it eventually becomes SAR. As you can see, the enzyme responsible for this conversion is GNMT, this one here. And this plays an important role in removing excess SAM by catalyzing the methyl group transfer from SAM to glycine. and that ultimately forms sarcosine. So this removal process is downregulated when there are low levels of methylfolate and SAM levels. Again, the same sort of function, trying to maintain homeostasis constantly. SAR, S-adenosyl homocysteine, is then hydrolyzed to homocysteine, which completes the methionine cycle. And this reaction is readily reversible, but the dynamics strongly favor the production of SAR, and therefore any elevation in homocysteine will consequently lead to an increase in SAR. And SAR is a potent feedback inhibitor in methyltransferase enzymes or reactions. Its pathogenicity lies in its binding affinity for and inhibition of methyltransferase enzymes within many tissue components. And that includes DNA, RNA, phospholipids, and many others. And it's for this reason that plasma levels of SAR have been shown to be a more sensitive marker for clinical cardiovascular disease, renal disease, and Alzheimer's disease than plasma homocysteine. Methylation reactions ultimately depend on SAR removal, and as you can see, it also relies on the functioning of the AHCY enzyme, as you can see here, which is dependent on the availability of B3 for its functioning. So finally, we come to the final part of this webinar, where I will cover the transulfuration pathway. So as you already know, transulfuration is the main route for irreversible homocysteine transulfuration or homocysteine disposal. It connects methylation, mitochondrial energy production, and glutathione biosynthesis. So transulfuration occurs when a sulfur group is transferred to various molecules, such as to cystathionine. As you can see, that's the first step here in the transulfuration pathway, and then to cysteine on either side here. And that ultimately either ends up in the biosynthesis of glutathione, as well as pyruvate and taurine. This process is upregulated when needed, such as when the body is under oxidative stress and therefore glutathione demand is higher. And alternatively, transulfuration will also contribute to energy production when glutathione is not in high demand. As you can see, one of the molecules created in this pathway is pyruvate, which plays a major role in cell metabolism, and it fuels the citric acid cycle and therefore ATP production. So as you can see, there is an enzyme that interconnects homocysteine to cystathionine, and that's the CBS enzyme, which stands for cystathionine beta synthase. And this enzyme, as you can see, has 3 cofactor nutrients, and that's B6, iron, and serine. So CBS is upregulated when excess methionine and SAM are present, which causes an increase in homocysteine conversion to cystathionine. And the opposite will also happen when SAM and methionine are low. So in general, literature on a SNP in this enzyme indicates that it has an upregulating impact, meaning that the removal of homocysteine via transulfuration is sped up. However, population studies show that a SNP can also lead to a downregulation in the enzyme, effectively leading to a backup in homocysteine and a potential lack of glutathione production. And as you can see, there are also a couple of other enzymes here that are important in this pathway, such as CTH and GSS, that also have an impact on glutathione synthesis. And you'll note that B6 is a cofactor nutrient here as well for these these enzymes. And so any insufficiencies in B6 will of course lead to a backup in this pathway, and therefore potentially an insufficiency in glutathione, as well as you could also say pyruvate. And you know, in my opinion, this is something that comes up very often, particularly after seeing many reports on the metabolomics and Nutrival panels, which many of you may be familiar with. And B6 often is highlighted as insufficient for many people. So I think it's a nutrient that's often overlooked. So glutathione, and I'm sure many of you already know about the importance of glutathione, but I needed to, of course, make it part of this presentation because it's such an important outcome of the transulfuration pathway. So it is essential for neutralizing hydrogen peroxide and lipid peroxides through GSH peroxidase reactions. So hydrogen peroxide and lipid peroxides are two markers of oxidative damage or oxidative stress. And the level of those products are directly related to the level of glutathione because it's so important in reducing those products. It's also involved in phase 2 detoxification by conjugating hormones, toxins, and xenobiotics to make them water soluble for excretion. So with methylation underpinning so many processes, the big question in practice is when to test. And what kind of clients or patients would we choose to use this test on? So going back to one of the slides at the very beginning of this presentation, let's look again at some of the processes that methylation plays an important role in. So we have creatine production at the top, which is a substance found naturally in muscle cells, as we've already mentioned. It helps your muscles and cells produce ATP. So in the case of chronic fatigue or poor exercise tolerance, looking into methylation may be a good idea. We also have problems with DNA and RNA synthesis, as well as gene regulation. So conditions such as cancer are highly implicated here. And then we have, the role that methylation can play in hormone regulation and also detoxification of environmental toxins. So we have key issues such as hormone imbalances, symptoms of estrogen dominance, for example, PCOS, PMS, and so forth. We then also have the importance of cell membrane repair myelination when it comes to methylation and the role it plays here. So in the case of this section, we're looking at neurological conditions, so issues such as Parkinson's disease, for example, as well as other neurological diseases that can be highly related to poor methylation. Those with mental health conditions such as depression, anxiety, bipolar, schizophrenia, and other mood disorders may also have methylation defects due to the role that methylation plays in neurotransmitter production and catabolism. And then finally, we have cardiovascular disease because of the fact that methylation plays an important role in endothelial function and nitric oxide production as well. So before I open the floor up for questions, I wanted to go over some of the common barriers to optimal methylation to further elucidate what kind of patient you may want to be offering this test to. So at the top, we have GI dysbiosis. Studies have shown that those with microbiome imbalances, there is a consequent impact on DNA methylation, as well as the role that certain organisms, such as lactobacillus and bifidobacterium species, play in the role of folate production, and therefore the contribution to circulating folate levels in the body. And of course, that relates to methylation capacity. We also then have increased oxidative stress, which we know has been shown to affect the function and activity of enzymes responsible for regulating DNA methylation. Stress is a huge one as well, and particularly where the studies are highlighting is early life stress, such as childhood abuse and trauma, adverse childhood events, etc. And the lasting effects on methylation that can persist into adulthood. We then also have exposure to environmental toxins, which I wanted to do a separate slide for here, just to illustrate the impact of environmental chemicals on methylation. I found this great illustration, and the illustration is referenced here. And this illustration highlights the effect of common toxins on our methylation capacity. So environmental chemicals have been linked to aberrant changes in epigenetic pathways, both in experimental and epidemiological studies. And this here is an overview of possible mechanisms of action for environmental chemicals of DNA methylation based on reviews of these experimental studies. So as you can see, we've got heavy metals, persistent organic pollutants such as pesticides and PCBs, polycyclic aromatic hydrocarbons, which all increase reactive oxygen species. And this leads to an elevated demand of glutathione conjugation. So glutathione will conjugate the reactive oxygen species, chemicals, and their metabolites. And so therefore, what happens is homocysteine is shunted towards glutathione production instead of methionine synthesis, effectively leading to a reduced synthesis of SAM. And of course, SAM depletion thus inhibits or potentially inhibits DNA methylation and therefore leads to a picture of hypomethylation. As you can see, exposures to specific environmental chemicals like short-term exposure to cadmium, polycyclic aromatic hydrocarbons, lead and mercury can actually directly reduce the enzymatic activity and concentrations of enzymes like DNMT, which is the enzyme responsible for DNA methylation. So quite an important thing to highlight really is just how impactful our exposure to these common toxins can be on methylation capacity. So just coming back to this slide, we've already spoken about the impact of nutrient deficiencies, especially those that are cofactors for methylation enzymes. What about sleep? So there is substantial evidence to suggest that DNA methylation is critically affected by sleep, and individuals that are subjected to both acute sleep deprivation as well as chronic sleep deprivation have changes in their epigenetic landscape. And so altered DNA methylation patterns have been observed in genes involved in metabolism as well as circadian genes. And then finally, we have medication use, and common medications such as antacids, non-steroidal anti-inflammatory drugs, glucocorticoids, methotrexate, for example, have all been shown to inhibit DNA methylation. So just in summary, and just to condense the info from the last few slides, and this again is a bit of a repetition here, but I wanted to put this here in one place so that you could have this for your reference. These are the types of patients that can benefit from the methylation panel. And of course, because of the all-encompassing role that methylation plays in basic human physiology, the range of symptoms associated with methylation defects is very broad. And so again, those with questionable detoxification, those with a risk of cancer, perhaps a family history of cancer, cardiovascular disease, psychiatric and mood disorders, neurological disorders, as well as chronic fatigue may all be interesting case studies to test methylation on. So there we finally come to the end of the presentation. Please write your question in the question tab on the GoToWebinar control panel. And I'll start to sift through the questions as soon as I see them coming through. If you have any questions that you want to ask the team personally, you can get in touch via the email that's given here, clineduk@gdx.net. Any feedback would also be very much appreciated. Let me have a look and see what questions that we have so far. Okay. So just so you all know, there is a recording for this webinar. So for anyone asking that question, just so you know, you will receive a recording, and the slides will also be sent to you in PDF format. You may also note that the methylation support guide is in the handouts section on the control panel, but you will receive the slides separately in a separate email. Okay, so I have a question here. So someone is saying they have very high cystathionine with a potential upregulation of CBS. Cysteine level is just below reference range, homocysteine just in RR, I'm not sure what that is. Would this indicate an issue with CTH? And any suggestions how to reduce the cystathionine and increase the cysteine? So the junction between cystathionine and cysteine is the CBS enzyme. And that enzyme, as you would have noted, is dependent on the availability of B6 particularly. Then you've also got iron as well as serine, but B6 is an important nutrient. So if you have an elevation in your cystathionine but low levels of cysteine, this is suggesting that there's a backup in that pathway, and potentially because of a lower availability of those cofactor nutrients to help the activity of that enzyme function properly and continue the flow downwards eventually into glutathione production. Just sifting through the questions here. Okay. So someone's asking about preparing a client for the Metabolomics Plus test. So the Metabolomics Plus is a urine test, and there is a page on our website. So the page for the test, the Metabolomics Plus, will give you some preparatory guidelines, which I would recommend that you look at. Alternatively, please do send us an email. So someone's asking an interesting question here. Do you commonly see an increase in ammonia when people have CBS SNPs and SNPs to BHMT? And would this also put pressure on the urea cycle resulting in BH4 deficiency? So in our methylation panel, we don't test ammonia. However, theoretically, an upregulation in CBS may lead to an increase in ammonia, and of course, yes, this can have an impact on BH4 and the production of BH4, as well as putting pressure on the urea cycle. I often find that when you're getting symptoms of high ammonia, for example, you're suspecting that that's going on for a client or patient, that can be mainly related to GI dysbiosis. And the overproduction of ammonia through the presence of dysbiotic bacteria. So that's definitely something to consider in relation to that, and not just methylation. And I should also add that with the CBS, because there are, that you've got research suggesting that there is, when there is a SNP on that, there's an upregulation, but we can also see a downregulation. So that's why it's quite important to see what the functional analytes around that enzyme are doing, such as the cystathionine and the cysteine. So I would recommend, if you haven't already, considering to do this test so that you can have a look at whether that SNP is actually playing out in real time. So for clients that present with chronic fatigue syndrome, how can we use the methylation panel to help them? So If you will recall, there are various methyltransferase enzymes that are important in relation to various aspects of health, energy production, as well as cellular membrane health, nervous system health, creatine production as well, which is important for ATP as well as muscle recovery. So if you were to do a methylation panel on a patient that has that clinical presentation and they were to show a picture of hypomethylation, so in this regard that would mean lower levels of SAM, you would be looking at supporting them through making sure that they have the right cofactor nutrients there present for both the folate and the methionine cycle to support them in producing optimal levels of SAM. As well as making sure that there aren't any SNPs that are potentially going to slow down or down-regulate the production of SAM. So that's sort of roughly how you would approach it. And of course, there are other means as well, but specifically related to methylation, that's what we would look at. So how is the test taken? That's a very good question. So the test is a combination of a blood draw as well as a buccal swab. So it combines both the functional analytes in blood sample and the buccal swab is of course there to test the SNPs related to various parts of methylation. I should add that the genomic markers are an add-on to the methylation panel, so they're not automatically included. If your client or patient hasn't done their genes yet, hasn't tested their genes, then I would highly recommend doing that because you'll be able to see which SNPs are having an impact on which parts of the methylation cycle and how they may be impacting certain analytes. The test, yes, it does require immediate centrifuging, so that's important to consider when organising a phlebotomy appointment for your client or patient. So someone's asking if I would consider or recommend testing for mast cell activation syndrome, and that's absolutely yes. You may recall that one of the methyltransferase enzymes is the HNMT enzyme, which is related to histamine detoxification and metabolism. And we also have other things as well. So poor detoxification as well can be related to methylation, and that is highly related to MCAS. So yes, absolutely, I would recommend testing methylation for that clinical presentation. So another question is related to the supplementation of folic acid. So someone's asking how much dietary folic acid is too much. So that there isn't actually an upper limit for dietary folic acid, that you can never really get too much in the diet because dietary folic acid, or folate should I say, doesn't have a negative impact on the enzyme, on the DHFR enzyme. It's supplemental synthetic folic acid which has a down-regulatory impact on that enzyme, but dietary intake won't do that, so there is no risk there whatsoever. In terms of the upper limit for supplemental folate or folic acid, it's 1000 mcg. That at least is the sort of governmental sort of set guidelines. And you may recall back at the beginning of the presentation, I spoke about the risks of, if you're supplementing with, for example, folic acid, the risks of unmetabolized folic acid are mainly related to those supplementing with higher than 1000 mcg. So I've got a question here related to supplementation around glutathione or NAC. So to help improve glutathione, so a practitioner here has done a NutriVal test for their patient that has a high sensitivity to histamine, and her glutathione came back very low, oxidative stress very high, which is unsurprising. So the question is whether to prescribe glutathione directly or NAC. And this is just my personal opinion, and it may be different for others, but I would say both is if someone has very low levels of glutathione and high levels of oxidative damage markers, then supplementing both NAC as well as glutathione is probably a good therapeutic focus, at least initially, to try to get levels up to a healthy amount initially, and then you may want to just switch to one afterwards once their levels have improved. Okay. How can you evaluate the SAM to SAR ratio with a client? So we'll be going through this in next week's presentation. One of the ratios that we highlight in our methylation panel is the SAM to SAR ratio, which is a universal way of testing the risk of hypo or hypermethylation according to the levels of both of those compounds. So that is measured in our methylation panel, and you will be able to see a little bit more about that in next week's presentation. So I've got a question here to clarify the relationship between cancer and methylation. So you will recall that there was a short sort of description or insight into the enzyme SHMT, which is in the folate cycle, and this particular enzyme, it does two things. Depending on the demand for methylation, it will either help to produce 5,10-methylene tetrahydrofolate for the production of 5-THF, or it will be shunted down the purine nucleotide synthesis pathway. And that pathway leads to, has an impact on DNA methylation, DNA regulation, and repair. So essentially what I was explaining is that any SNPs on that enzyme, which has a down-regulating impact on that enzyme, can be related to issues with DNA repair and DNA regulation, and that has a sort of a pivotal role in the development of cancer or the risk of cancer. I hope that's clarified the question. So the safe upper limit of 5-MTHF is the same, so it's 1000 mcg or UG, depending on how you measure it. It's the same as folic acid. So I've got a question here on my opinion of using molybdenum to help the CBS pathway. So molybdenum is an important nutrient for detox pathways in the liver, particularly sulfuration. And I think it goes back to the question around, whether a CBS SNP will lead to an upregulation and therefore poor ammonia detoxification. And molybdenum will help to improve that. But again, I think it's important to not just go by what the genomic markers are saying, but to look at the functional analytes around those enzymes to see whether that marker, or that SNP, should I say, is being expressed, and what's actually happening in that sort of dynamic interplay between those pathways. Another practitioner is asking about a client with high sarcosine and what are the potential solutions for GNMT SNPs. So high sarcosine can often be indicative when there is an upregulation in methylation, and potentially because of an upregulation in GNMT. What I would say is that this can be also related to pathways a bit further upstream. And so if you're looking at, for example, the BHMT pathway and how that's functioning, that might help to elucidate a little bit more about why there may be an upregulation in the GNMT pathway. The short answer is that just check what the SAM levels are like. Because if they are normal, then this may be just a a sort of compensatory mechanism to prevent hypermethylation from occurring. So check the SAM, check the SAR, because ultimately it's the outcome of those two compounds that are going to determine whether there is an issue with the outcome of methylation. Got another question about whether this test can be performed on children or teenagers. So the reference ranges are for an adult population, so that's something to mention. So that's 18 upwards. So depending on the age, basically. Of course, it also depends on the child's sensitivity to having a blood sample taken. That's always going to be a bit of a hindrance in testing. But I would say that because of the fact that the reference ranges are for an adult population, you may need to adjust accordingly to what it would be for a child if they were younger than 18, for example. So I've got a question here. Why is the enzyme AHCY not assessed in your DNA add-on? Good question. Thank you for asking a question. I do not know is a short answer to that, but I can find out, and I'll see what the outcome of that is. I'm not sure why. I'm sure there is a good reason, but I will find out and I'll come back to that definitely. Okay, I'm going to just answer one more question here and then we'll wrap up for today. Okay, so I've got a question here. Which supplements do you recommend in a patient with both MTHFR and COMT enzyme SNP? So we know that the, for example, the cofactor nutrients for COMT are magnesium and also B2, zinc, and SAM. So you can supply them with the nutrients, but you'll need to make sure that they are, of course, that they're producing enough SAM. If they're not, it may be related to the MTHFR SNP that's downregulating the availability of 5-MTHF, in which case you could supplement with methylfolate if they are there, you know, if they do have low levels of SAM. So again, definitely test the functional analytes to see whether those SNPs are being played out. With the COMT enzyme, if they have a SNP on the COMT enzyme, then mainly you will know that it's being played out because they will have elevated levels of anxiety and problems with downregulating their stress response, as well as potentially, if they are a female, issues with estrogen detoxification. So thank you so much for your time today. It is much appreciated. I hope that was an informative webinar. Again, you'll receive the recording later on today, as well as the slides. Please do join me again next week, where I'll be talking more specifically about our methylation panel, and then we'll be talking through a couple of really interesting case studies where methylation testing has proven to be very valuable. So thank you once again. Have a lovely day and see you next week.